Hello, everyone, and welcome to the Audio Product Development Alliance. I'm Roger Shively from Shively Acoustics International, and this is the APDA, your gateway to audio product development. It's the only organization focused exclusively on audio product development education, providing current and relevant content that can be experienced in person, live online, like now, or later on demand. It's combined with a cross-industry knowledge sharing. The APDA serves as a networking hub for the audio industry, offering access to experts, as we have one with us today, and colleagues for professional development. The APDA is where we come to learn, to build relationships, and also better audio products. We talk about design, measurement simulation, supply chain, automotive application, headphones, earphones, wireless technologies, and we even touch on industry standards. Online with us today from the APDA are Steve Willenberg from LinkPlay. Hi, Steve.
Hi, Roger. How you doing?
I'm doing good. And Dave Lindberg from DB Enterprises and the THD Podcast. Hi, Dave.
Hello, how is everybody?
And our media partner, Joel Martins from Express, is behind the scenes, as well as Adam Levinson from Levinson Consulting, working with us behind the scenes. And also like to thank Spencer, who is producing us tonight on this live talk. We are recording this as well, so you can check it out on the YouTube channel. You should share it, like it, and join us often. Next month in May, we're going to be talking with Dave on manufacturing in the South Pacific Asia. I believe that's Fujicon. And
Yep.
later in June, we'll have the Audio Foundry join us and meet with them. And then in July, we're looking at Bluetooth LE audio again. And then in August, we're going to be revisiting tariffs, as we did earlier, to see where we are at any given moment, see how we're doing. But today, I'd like to welcome in today Dr. Jan Rennies-Hochmuth. Hopefully I got that right. Head of Personalized Audio and Personalized Hearing Systems, at the Fraunhofer Institute for Digital Media Technology. That's the IDMT. Hi, Jan. How you doing?
Hi, thanks. I'm great. Pleasure to be here.
Yeah, so today we're going to talk about sound personalization in audio products. And, every person experiences sound differently and has their own individual listening preferences, and which can also depend on age, and hearing ability. Therefore, factory settings for audio solutions can't equally be applied to all listeners or be appealing to them. So the usual adjustment options just have some limitations also. So today, we'd like to talk a little bit about personalization. It's a little striking that audio playback personalization has not actually received more attention so far. I mean, the concepts have been around, but more advanced audio features allowing dynamic adjustments of audio playback in an environmental condition such as a noisy vehicle are typically just applied in a very generic and non-individualized way, I think, as you know. So let's learn a little bit more. If you're ready, Jan, we're ready. So let's let you jump in. If you got some things you want to share, let's go ahead and do that.
Okay,
And here we go.
I'll do that.
There we go. Looking good.
Okay, perfect. Yes, welcome everybody to this webinar. I'm excited to be here. I've been interested in sound personalization for my whole academic and professional life in a way, and I would like to kick off this webinar with an anecdote. When talking about individual listening preferences and the challenges that come with them, many people think of preferences, or when they think of preferences, the first thing that comes to mind is hearing threshold, which is certainly relevant, but by no means the only factor, because if it were, then sound personalization would be exclusively relevant for people with hearing loss, which is certainly not the case. I will briefly run through a couple of studies we did on investigating all these features. Then I'll come to some methods that are used or can be used for sound personalization. And in the end, I will look at some application examples. Please feel free to jump
Yeah.
in with questions and discuss at any time. This is really meant to be an open platform, and I'm really looking forward to getting your thoughts on these topics as well.
Yeah, and if anyone's watching online in the on the live chat, if you put something in the chat, we'll make sure that gets to see it and hear it. So please go ahead.
Okay, great. Thanks, Roger. Okay, so I'd like to share this anecdote. So we used to have this one demo on public house days when we had the general public come to our institute and visit and look at some demos that we built from our research. And one of the demos was that we had people sit on a desk, they listened to some stimuli, for example, speech, and we gave them a tool to adjust the sound of the voices on a two-dimensional interface, such as this one, where they could kind of move a dot on a two-dimensional screen, and moving from left to right would change kind of the spectral tilt of the voice, and moving up and down would change the speech volume. And then we asked them to just play around, explore the space, and stop wherever they thought they liked it best. And all these little crosses that you see on the gray square here is some points along this parameter space where people thought, okay, that's how I
might
like
need to
it.
share again, Jan, because I think we lost it.
Oh, that's too bad. It still says I'm sharing. Okay, let me do that again. I'm sorry.
No,
As you can see it? Okay.
it looked
Okay.
fine.
Looking
Maybe.
good then.
That looks good.
Now we're back.
Okay,
Yeah.
perfect.
Now it's back on. We lost
Okay,
it
thank you.
online. So thanks. Okay.
So these little crosses here are points where people said that's the preference point I have, and there were some who really liked a lot of low frequency amplification and very high volume, and some were in the really opposite corner of this parameter space. So the point I'm making is that this is something we saw every time we had this demo. So people really do have different preferences when you give them the exact same stimuli under the exact same conditions. And that's not something which is only observed anecdotally, but also some studies, some scientific studies have looked at that. And for example, Völker and colleagues hypothesized that individual sum preference judgments are based on different individual weightings of prototypical subjective traits, and they suggested some dimensions along which people and their preferences could be sorted. For example, some would tend to adjust sound to be more intelligible, whereas others might tend more towards listening comfort. If you have algorithms that reduce noise at the cost of also introducing distortions, then some would prefer more residual noise but better quality, and others vice versa. Some might like it very loud, others not so much. Then there's the spectral balance. So there are different dimensions along which preferences can differ between people. And there are several studies which basically all found that under the same conditions, differences differ a lot. So that's an earlier study of ours where we had a similar setting as before. So loudness on one axis and spectral balance on the other axis. Again, large spread all over the place. PhD student of mine did this with hearing impaired listeners and also found a lot of spread across the entire parameter space. Other colleagues from Denmark and our work looked at strength of noise reduction algorithms and found that people really did prefer their self-adjusted noise reduction strength when they were tested blindly. So they differed along this noise hater, distortion hater dimension. And all of these previous studies were looking at speech stimuli, but the same is also observed when we have music as the target stimulus. So that's data a student of mine collected 10, 11 years ago, and she gave people, again, a two-dimensional space, and then people could adjust the spectral tilt as well as the mid-frequency amplification or attenuation using the same two-dimensional interface. And for music also, most people were somewhere, at least in the, say, upper half of this parameter space. But the point is there was no single spot, like you said in the beginning, Roger, that would satisfy everybody equally well.
That's interesting. And then I suppose you'll explain it, but then figuring out what it is that makes the difference and how address that.
Exactly. So that's the question. I mean, if you see all these data clouds really, where there is no apparent trend or sometimes not even a sweet spot, is it just a random variable? That's, I think, maybe a fair question to ask. So is preference just something which changes from day to day and which you would have to reassess every time you set up an audio system? That will be bad, of course, when you are in product design and want to make it the best possible experience. But according to our own experience and also what others have found, that's not the case. So there are a couple of studies that have looked at retest comparisons when people adjusted or had means to adjust audio to their own liking on different days or early in the morning and then later again, or even after some weeks or month. And there is many examples where people have found that what listeners adjust for themselves according to their preference is reasonably stable. So, for example, Kubiak and co-authors found that for speech in different scenarios, differences in adjustments over a broad range differed by no more than 2.5 dB on average. The noise reduction strength studies also re-invited subjects after a couple of weeks and found that, again, this individual setting was stable. Jonathan Gersmein found the same for hearing aid settings, where people, again, approached very closely the settings they had made the week before. And in a study that I will be looking into more detail in a minute, we also found very high correlation and low offset from test to retest session. So this picture here, this figure here shows adjusted levels where people self-adjusted sound. I will go into more detail later on one day, and then 1 week later they came back and did the same, and that's plotted on the x-axis here. So an ideal agreement would be on the diagonal, but as you can see, it's clustered around the diagonal, so there's no offset or no general deviation, and that's what we often see, and not only for levels or loudness, but also for spectral changes, spectral tilts, or by in terms of strength of dynamic range compression and other audio modification schemes. So in general, what we usually find is that there is a large variance between people, but within one listener, the preferred settings are reasonably stable when you retest them under the same conditions.
And it's retested. How
Yes,
many
please.
times typically did the studies retest somebody?
Most studies only do it twice, so test and
Okay.
retest. We had a study once where we had a retest after 1 week and then another after 3 months, and we
Okay.
also found kind of long-term in the
Yeah.
sense of several weeks stability and to a similar degree.
So you still don't see any randomness, no matter, even if it's just two, you're pretty confident that you're getting a real picture of that individual. Okay, good.
Yeah, I would argue. Yeah. So, and then that's what you were asking about. So, what is it that drives these big differences that we see between people? So, or vice versa, when we are product engineers, how can we grasp these individual preferences and turn them into tunable parameters in an audio product? Because essentially that's what we are after in the end. And unfortunately, that's more tricky. So again, there are a couple of studies from which I'm quoting here. And for example, Nea and Wagner found that preferred noise reduction strength is not easily captured by any of these factors. And they looked at audibility things, sound personality questionnaires, cognitive measures, psychoacoustic sensitivity to certain sounds. Similarly, this study found that there were only very poor correlations between different measures derived from the audiogram or age or speech recognition performance with the self-adjusted preferences of their participants. And a study from Minnesota also agreed with that, and they found that the gain that people adjusted for themselves was not really related to any of these factors listed here, so nor to age, gender, hearing threshold, or the time they spent on these adjustments. So it's not easy to find this one question that will tell you what preference a certain listener has, and consequently, it's not straightforward to tune an audio system.
This kind of goes to your point that it's not just threshold, because you'd think, hearing loss, maybe the gain would be different because of that, or it be in a different way, but it's pretty specific to something that's not age or hearing loss related. It's interesting necessarily.
And I think it's fair to say that it's really unknown so far. So from a scientific point of view, we don't know what is driving individual preferences.
Right, but
and also there is not really a simple test which we can use to get to individual preferences.
okay.
There is, of course, a lot of tests for measuring hearing threshold, and I will be talking about the role of hearing threshold a bit now, because of course, that's a relevant factor, right? So, I mean, for everybody who is not so familiar with this concept, the hearing threshold is usually measured in terms of an audiogram, with 0 dB hearing level line is kind of the average healthy adult, and you look at audibility or just audible levels of narrowband stimuli at different frequencies, and any deviation from this average population is plotted downward, so upside down. So this red dot would mean that this person here on the right ear requires a 25 dB higher than average level for a 250 hertz tone to be audible. And the shape you see here and in red and blue is a typical age-related hearing loss where you lose sensitivity in the higher frequencies, which means that these fricative sounds, for example, like in sh, they would be inaudible at a normal speech level for this person because they are above the threshold. So the first thing, of course, when you have such a listener, an audio product must do is amplify everything to reach supra-threshold levels for this individual listener. And as you can very clearly see, this amplification has to be frequency dependent, so lower amplification in the low frequencies, because typically hearing is closer to normal thresholds there than at higher frequencies. But of course, then amplification also has to be level dependent, because the point at which sounds become painfully or dangerously loud does not shift linearly with the audiogram. So typically at 100, 120 dB or so, that's where the discomfort or dangerous levels start. So you have to compress stimuli where you apply amplification, or in other words, the amplification you provide is frequency and input level dependent. So that's what the typical hearing aid does as a first order hearing support, pushing everything above the threshold but not making it too loud. So that's that, and there are great tools available, apps and websites and screening tools where you can measure or estimate your thresholds, and that's of course relevant information. And the first thing an audio product has to do is ensure that everything is actually audible. So that's critical, but I have one very, I find, striking example in the next slides that show that it's not sufficient to adjust the system to preferences. And that's from a study, it's also a couple of years old by now, where we had a hearing aid-like technology implemented on a telephone server. So people at home could call a telephone number from their landline telephones, and then they would listen to some speech recordings that we provided, and they could use the keypad to adjust the sound of the voices they heard using presets, which would provide more low frequency amplification or more high frequency amplification, and turn the volume up and down. So again, a two-dimensional space, but with a kind of button discretized way. And we had people that had a typical age-related hearing loss, so that's the average and range of hearing losses here. And then we had them listen to 6 different audio scenes, different codecs, different qualities, noise in the background, and so forth. And they did these adjustments for each scene, and we stored the settings, and then in a blind test had them compare the original and the individualized settings, and we found that, yeah, in general, they liked the self-adjusted sounds better in this blind test. So that was fine, and as we had hoped. But more interestingly was the way they adjusted these sound scenes, and that's illustrated here. So again, you have the hearing threshold distribution of our 25 listeners here. So all had this relatively similar high frequency, slow pain hearing loss. So coming from a hearing aid mindset, we had expected their self-adjusted settings to be distributed something like this. So because all had a high frequency hearing loss, we would have expected everybody or most people to select a high frequency amplification, maybe a flat one, but not so much low frequency amplification. But in fact, that's what they did. So most of these listeners went for low frequency amplification, and very consistently so. So when we first saw this, we had them redo these adjustments because we thought we had made a mistake here. But they were very clear about what they preferred, and that was puzzling. And then we looked deeper into, okay, maybe they're not so similar after all. So we looked into these different people who did adjust the high frequency amplification, and they were actually the ones who had the lowest high frequency hearing loss. So there was really a kind of negative correlation between the degree of high frequency hearing loss and the preference for high frequency amplification. So that was a very striking example of where the threshold based setting would even make people very unhappy in that case, not only not agreeing, but pointing in the wrong direction.
Is that, you think, like, maybe you'll get into it later, but typically hearing aids are always complained about because it's not quite doing the job that the user wants to use it for, and perhaps it's just when threshold is all it's considering, it's creating a problem, period, for the listener, and then they stop using the hearing aid. So I wonder if that's the case. Do you have any experience in that?
Yeah, I mean, of course, hearing aids do more than that, and it's don't only measure the hearing threshold, but people spend a lot of effort into better tuning of hearing aids, and usually there's an expert, and it takes a long time after measuring the hearing aid and providing kind of a first prescriptive gain rule.
Right.
Then the real work only starts, because probably due to effects as we have seen here, and like you mentioned. There's this back and forth. People go home with the hearing aids, experience it in their real life, and they go back to the hearing aid dispenser or clinic, and then they describe their impressions, and then the expert has to kind of make sense of what they say and readjust these parameters. And then there's a back and forth iterative procedure, and hopefully in the end you have a better setting. But you're right, it's very complicated, and many people are not
Patient.
really happy. But one reason also is that, of course, hearing aids are most needed in very difficult listening conditions. So when there's a lot of background noise, multiple talkers, and then these kind of standard settings like multi-channel dynamic range compression, they are not very effective in improving intelligibility, for example.
Right.
And you need advanced algorithms. So there's a lot of different technologies that interact and have to be tuned individually.
Yeah, hopefully this will guide some of those products to a better solution, because some of them I think are just a little too simple, and they have no opportunity for doing what we're talking about here, making it a very personal listening experience.
Yeah, but the tuning really is key. So and also, I mean, what comes together is that many people who have a hearing aid are maybe not very willing, or maybe not even capable to handle complex technology very well. So it's tricky for them to do that themselves. So they need the expert, and it's an effortful way to get a proper tuning. Okay, so maybe as kind of an interim summary, I'd like to point out that some personalization can be done along many different dimensions. There is, in terms of preferences, not really such a thing as normal hearing. And also preferences are different both between people with clinically normal hearing and people with hearing loss. So there's not having or not having a hearing loss does not mean preferences are more or less similar. It's just one other individual factor. It's currently not known what's behind these differences really. What is, I think, very clear is that the playback volume differs and makes a difference. So imagine you listen to music at a very soft playback volume and you have a high frequency hearing loss, then of course you have to crank up the high frequencies to make the violence audible in the first place. But then when you listen to music at a very high volume, does not mean that automatically you would prefer a very high frequency amplification. So in other words, at lower levels, the hearing threshold matters, and at higher levels, like in the telephone example, it does not really, or at least it cannot be used to derive individual predictions. So in my opinion, the studies so far show that the best thing you can do in audio products is to find good ways for self-adjustment, meaning that people can tune the sound to their own preferences using suitable interfaces and methods. And yeah, that brings me to this third part, where I want to look at some methods that have been used or can be used for sound personalization in audio products. So that's the 1960 radio.
Okay.
And I put this in to remind us that, of course, sound personalization is nothing that we have invented, but it has been with audio products basically from the beginning. You could change the volume, you could change some EQ settings, and one very frequently used concept were such presets, bass, solo, jazz, classic, orchestra, whatever, you've seen them all.
Yes.
It's easy to use, that's for sure, but also maybe you would agree that they are not entirely intuitive, so people don't really know what's happening under the hood when you press jazz or orchestra. And also these kinds of concepts would be ignorant towards any individual factors such as hearing thresholds, for example.
Right.
On the other hand, hearing threshold based systems would ignore supra-threshold preference settings. So many options that you find these days or in the old days are either limited because they're only looking at certain aspects of preferences or not very intuitive. And one example is a 2009 car radio. It's from my boss who took the effort of kind of noting down all the different options you had in his then modern car radio. So you could adjust these different settings here, each with different steps from, for example, -7 to 7. And then you could go to in the menu one menu level deeper, which was called enhance. And then you had all these options. And then somewhere in between, you had these old presets. And of course, they were all somehow accessing the same things. But I mean, when you have that in different menu levels, it's,
You
I
get
guess,
lost.
yeah, not very. You get my point, right? So
explaining
it's very
bass,
easy.
X bass, and enhanced bass. My goodness.
Yeah, so it's very easy to overwhelm the listener. You provide many options, but then the typical user will not, or maybe once take the time to go through each of these, but certainly not in a very systematic way, or they can get easily frustrated. So that's maybe also not the way to go. So the general challenge here is that there are many parameters, and all of them will affect how you perceive sound. They can include frequency-dependent amplification, parameters of dynamic range compression, including time constants and aggressiveness and so forth. And tuning those to the individual listener is required to some degree to achieve acceptance and an actual benefit. But you must be careful not to overwhelm the listener and create inaccessibility, really. So what can you do, really? So you can, of course, have the expert, similar to what's done in hearing aids, where you have a whole professional infrastructure. You go there, you're taken care of, you run many tests, and then the expert does the actual fitting. But that's not a very promising approach when you're in maybe automotive or consumer audio product domain, because sadly, hearing aids still come with a certain stigma. Many people, you saw it already, that many people are not satisfied. That's one reason for not wearing them, but many people also don't use hearing aids, even though they would benefit, because they are still so stigmatized. And that's an image that typically consumer products would rather avoid. So kind of doing a clinical audiogram-based sinusoidal hearing test like adjustment is not very sexy, maybe in a high-end audio product. The other way is to kind of not use an expert, but give the users full control. But then, of course, thinking of the example I just showed, with a strongly reduced degree of freedom in terms of what you can actually adjust using some well-selected options only. And I want to go through one study we presented at an AES conference a couple of years ago, where we looked at different options for finding individual preferences. So we had back then focused on people with hearing loss and speech as the target signal, and we compared different interfaces to find different parameters for the same hearing support algorithm. So that was a classic hearing aid multi-channel compression algorithm, which was parameterized by different user interfaces and by the same users also. So the only difference really was the type of interface, which was what we were interested in. One of these interfaces was rather clinical. We put this in for comparison. So that was based on loudness perception. So not only threshold measurements, but also individual loudness perception, and then trying to get it back to a normal reference loudness perception corresponding to the average normal hearing listener. Another one was what you also find in some hearing aids or other products, where people are given two choices, so two different signal processing versions of the same stimulus, and you can toggle between these two, and then you click the one you like better, and then in the background there's an adaptive algorithm that converges hopefully to some setting which matches your preference. So it's a very kind of guided procedure, very simple to use for the users. And then we had two interfaces which we called kind of real-time self-adjustments. One was the two-dimensional interface I just mentioned. So you could move a dot and then parameters would change in real time, and you explore the space and just stop where you like it best. And we did the exact same settings and parameters, but with two haptic rotary knobs. So the two dimensions basically were mapped onto one knob each. And we played them different stimuli and derived these parameters. So for this kind of real-time settings, you have to come up with good presets. So we found that people were most happy when you can actually predict what's happening. So when you move from here to the right and it gets more high-pitched all the time and you don't like the change, you would stop here. You wouldn't go all the way here. And vice versa. So it's getting louder and louder as you move up. And if it's too loud already, you wouldn't move up further. So having kind of a perceptual continuity is something that benefits people because they find it quick and intuitive, and it helps them to find their preferred spot. And this is one of the studies where we found this high retest reliability, and also in a blind test, people liked better what they self-adjusted. But I want to get to two different aspects we also measured here. One is the duration it takes. So how long does it take to personalize the sound using these different concepts? So that's the duration in seconds here. And that's kind of the repetition of the self-adjustment that we did. So for the kind of clinical loudness-based measurement, we only did it once at the beginning of each session. It took about 4 minutes, so relatively long. For this paired comparison, people were somewhat slower in the beginning and then faster in the end. So there was something like a training effect here. It still took between maybe 1.5 and 2.5 minutes on average. And then these real-time adjustments, so the 2D one and the knobs, people were fastest and could usually find their preference within half a minute or so. So relatively quick way of getting to an individual preference.
So having a
Um,
knob is important.
Say again?
Just the pair comparison was with the knob, correct? The position, is that right or no? Did I misunderstand that? Was it easier for them to
And
find it?
so the knobs are the triangles here. Oh,
Oh,
sorry.
okay. All right.
So that's the duration, right? So that's 1.5 to 2.5
Okay.
minutes, maybe when they had this paired comparison kind of guided procedure. Because I mean, you need a couple of comparisons to converge in the
Right.
background to some preferred settings, whereas in this um, real-time thing, once people have understood what the dimensions are, they usually
Mhm.
find that spot relatively quickly. That's
Hmm.
usually what we find.
Okay.
Hmm.
Let's learn more about that. Okay.
We also asked them about usability. So we used the standardized usability assessment procedure and had them rank how they preferred these different interfaces. And this population that we tested here, that was 9 years ago now. And some of our listeners we had explicitly selected to be kind of not very technology ready, if you will. So some didn't have a smartphone, had never used a touch screen before. So in this population, we found that the knobs, so something you could really touch, was the
Right.
most preferred interface, closely followed by the 2D, so an actual touch screen based interface. So these two were similar and preferred compared to the longer and kind of more clinical or more guided procedure using the preferred preferences. So the loudness-based one was never ranked first, mostly ranked fourth or third. And the knobs and the 2D shared the first two ranks for most of our listeners, really. So it's something people could easily get accustomed to, even those which had a low technology readiness level
Mhm. Yeah.
or technology affinity, if you will. And then over the years, we had a couple of projects with different audio companies from the telephone domain, consumer domain, automotive domain also. And yeah, in the end, we have come up with a procedure which arguably combines the advantages of threshold-based assessments and self-adjustments. And that's the procedure I will briefly show here. So the idea is that when you, for example, listen to music at a soft playback level, then of course you have to ensure audibility and the hearing threshold is estimated in this procedure, but in a playful way, which you will see in a minute. But then when you crank up the volume, basically the hearing threshold is ignored by the system, and the self-adjusted preference are all that matter in the end. And there's a smooth transition between these two states. Because we were working with companies from consumer electronics and automotive, we took care to not include any kind of medical touch and make this really something that could be used and would be appreciated by hopefully everybody using it, independent of whether they had a hearing loss or knew about a hearing loss in the first place. And what this procedure really is an interface to existing audio processing tools that are already available in audio products. So really a multi-channel compressor as available in automotive amplifiers or headphones or whatever. And the procedure is meant to parameterize these systems. So what we do first is kind of a guided procedural fitting to derive individual parameters, and then we fine-tune this using a 2D interface, because many of our studies have shown that people really like it. And of course, using a touchscreen is very conveniently implemented these days in apps or in dashboards of a car. And then, for example, in the automotive context, when you want to readjust the sound settings, you don't run through the whole procedure from the beginning again, but you could jump directly to this 2D interface and do some readjustments also while driving. So that's the general concept. The stimuli we are using here is not narrowband sounds like sinusoids or narrowband noises, but we use musical stimuli. And yeah, the one main reason is that we want to not include any kind of clinical touch to it. And we have recorded, for example, classic instruments like a cello representing the lower part of the spectrum, and a violin representing the upper part of the spectrum, and some bass and drum stimuli to kind of catch the edges of the spectrum. They are natural recordings, but we have processed them to kind of reduce this overlap somewhat, but they sound rather natural still. And really what the user does is kind of adjust the relative levels of these instruments to their own preference. And importantly, we do that at different playback volumes, at least two. So one rather soft, where we can get an estimate of the tilt of the hearing threshold, if there is any, and one at a higher playback level where we can really tap into the individual preferences. Are you a bass lover or a treble lover, for example?
Well, I have a quick question. Maybe you'll
Yes.
get into it, but how do I experience that as a user? I mean, I'm using my phone, or I'm using an interface in a car, and I'm listening to a
Yeah.
product I'm listening to the car, I'm listening to another product sitting on the table. How do I, or it's earphones, or?
In the actual two cases where this is implemented already in products, it's really the audio system that you are tuning to your own preferences, which plays the stimuli. So it's an automotive audio system where you have the app running in the head unit. So you do the adjustment of the stimuli while sitting in a car. It plays the cellos, it plays the violins. You do these adjustments. You are guided through the procedure. And in the other case, it's headphones, and there the adjustment is also stimuli are played by the headphones, and the adjustments are made in the companion app, where you do these adjustments. So
Okay.
same concept, really.
Are those two products in production right now?
Yeah, it's Mercedes audio systems where you can experience this, and also Sennheiser has integrated that into their headphones a couple of years ago. Yeah.
Okay, good.
And
Sorry.
yeah, no, it's good. So what you get in the end, really, from these adjustments is individualized, frequency and level dependent amplification parameters. And you ask what people are experiencing. So we start with the violin, and people adjust it to a preferred volume. Then the cellos fade in. Same thing. Then both are played at the same time, but it's a continuous music track. So basically, you listen to music throughout the whole procedure, and the instruments fade in and out, and you adjust the relative levels to each other, and also at different volumes. So it's kind of a holistic, continuous experience. And in the end, we get these parameters. So in a demo version, feel free to reach out, and I can send you a demo that's running on a PC. It's basically a slider where you do these adjustments, and then in the end, there's such a 2D interface where you can fine-tune sound. And then the settings are saved and applied when you listen to your own music in the audio system. So technically, what comes out of the procedure is basically parameters for multi-channel compressor, so knee points and parameters of a compressor settings, really. So for example, it could be implemented as a 3-channel system where you have low, mid, and high frequencies. And these may be extreme examples, but if you have a persona, a treble lover or a bass lover, but both have the same hearing threshold represented here by the red dots, then these two persons would receive very similar frequency-dependent amplification when the playback volume is low. But when the playback volume is high, then the top person here would get kind of a low frequency attenuation, high frequency amplification, and vice versa for the other person. So that's feasible, getting the same settings for low levels, because you need that in order for the sound to be audible. But then as you move to higher levels, this system would satisfy the preferences in the way that's adjusted before.
Okay. And then
That's pretty cool.
perhaps
And
you do you have examples of how you do that in a noisy environment when you're in a
Hey,
car or in a noisy
yeah,
room?
we
Oh,
do. So
oh,
I was coming to
what
that.
is just
Nice segue.
before we
yeah.
jump to that, is the your sound, is that the product that you would be marketing to like Mercedes and Sennheiser as you previously mentioned? Up on
Yeah,
the
that's
top
that's
right?
our
That
that's how we branded it, and that's how we use it. So that's the kind of the concept. And
hmm
Sennheiser and Mercedes are not calling it your sound. They call it
So,
sound personalization, or they have their own
okay, I was
Okay.
going to say if we look in
that
the
is their
menu, we
product.
won't see your sound, but we'll see something that
No,
represents your
but under
sound.
the hood is that
Okay.
Right.
for you.
Okay, it's good
Okay.
to know. All right, that's good to know. Yeah.
Okay, it's great to ask, Roger, because that's exactly, of
Oh,
course, what we were interested in. So
well, good.
when we started that, and the way it's currently implemented also in the Mercedes system is that people do this in quiet. So basically, when they
Yeah.
get that car or they get the audio system, they sit in the car, they do these adjustments, they guide it through the procedure, and then while driving, the individualized parameters are applied. Um, and of course, the car system, the audio system adjusts the sound to the driving condition. But this step goes on top of the individual settings that come from our procedure, and they are not individualized. So everybody would get kind of the same increase in volume and low frequency amplification as the driving noise increases on top of their own preferences that they set before. So that
Quick
part is
question.
not individualized.
I have a quick question. So
Yes, please.
earlier you mentioned, uh, did I understand that there's two sections where you do it offline in training, and then there was another one online? Does that apply to the training that we just went through here, this methodology for your sound, that there's offline measurements that you or adjustments that you're
Mhm.
planning for, and then
So kind of what I meant by offline is kind of the initial setup of the personalization. So this
right,
in this example, it's cellos and violins. In the Sennheiser products, it's more pop-like stimuli, but again,
right.
same concept. So more a high frequency representative and a low frequency representative. So this guided procedure of these instrumental stimuli, this is what we use, or what I call the offline thing. So when you set up your product, this is what you run through. And then maybe while driving or while being outside with your headphones, the readjustment you would probably only do using the 2D fine-tuning step rather than running through the whole thing again. So
Okay,
that's what
okay,
offline
but
is.
that's still an active thing that you would do with the product, as
Yes.
opposed to it being something that is like you were just talking about. The car has a noise profile, so you adjust to the
Mhm.
noise profile. Okay, all right, okay,
Yeah.
okay.
Okay,
Oh,
so what I'm telling now is basically a summary of a recent paper of ours, which was in the Journal of the Audio Engineering Society, where we looked at how noise dependent is that really? Because like I said, what we do or what's happening now is people do it in quiet, and of course, noise will somehow affect your sound perception. So the idea is, okay, what if you play back different background sounds? You run through your sound procedure several times with different background sounds, and then in a training mode, you learn the relation between the noise properties and your individual settings. And then later on, when you have actual real live playback usage of your system, you can somehow capture features of the audio environment and use that to better fine-tune the audio, not only individualizing the playback, but also adapting it to the current situation-specific listening environment. So that's the idea. Examples would be, of course, like you said, different driving noise conditions, or maybe when you have a speaker at home and you have different household noises that come up, or when you have a portable loudspeaker and you use it in different environments where, yeah, you could put a microphone on the device, monitor the environment, and then basically take this into account. The question, of course, was how does this affect? Is it okay to use a generic for example, speed-dependent adjustment of the sound? Is that fine for everybody or not? And to measure this, we collect the different driving noises in our car using a dummy head. We also recorded head-related impulse responses of given audio system, not a very high quality one, but that didn't matter because we were really only interested in the impact of noise. We recorded the driving noise in very different conditions, like idle mode and some fan noise, very low speeds, very high speeds. In Germany, you can go relatively fast, so you can record a lot of high frequency noise, also high level noise. So yeah, like you can see in these third octave spectra, these noises differed by a lot. And we then basically ran through this procedure that I just presented. So people adjusted the cellos and the violin several times with different noises played in the background. All were normal hearing, young adults. And we had 5 of these 10 conditions tested twice to also assess kind of the test-retest stability. And yeah, what we looked at in terms of references were these self-adjusted levels of the low frequency musical stimulus, the high frequency stimulus at a soft and a high playback volume. And yeah, so that's the stability first. So you've already seen this picture, so it comes from that study, and there was a very high agreement between adjustments in the test session and in the retest session, according to all statistical metrics, really, for the 5 conditions that we tested in both measurement sessions. And not only across all the 5 conditions, but also within each noise type, we found a high agreement between test and retest. And also within each listener, pooled across noise types, we found a high agreement. So we had a lot of indication that they were really adjusting sound to their preference, and they were stable in their preferences.
Okay.
And then, of course, we were interested in, okay, what does the noise do with the preferences? And that's a complicated plot, so I'll guide you through it step by step. So what you see here is the difference of the level of the violin and the cello. And 0 means they were adjusted to the same level, really, and positive values mean people preferred a higher level for the violin than for the cello sound. And the red dots here are the adjusted level differences in quiet for our 18 participants. So, for example, this person here preferred a very strong treble amplification in quiet. And most people actually, maybe a result of the audio system we used, but were positive, had a positive value here. So most preferred a slightly or much higher level of the high frequency stimulus compared to the low frequency stimulus in quiet. All the other symbols here are the adjustments in the different noise conditions, and to facilitate the comparison, we computed kind of the median value. That's the crosses you see here. So that's kind of the representative difference between high and low frequencies in noisy conditions. And the difference between these two, so how much did noise impact the adjusted sound balance, is plotted again at the bottom here. So that's these 14 dB or so difference. So in other words, compared to the adjustments in quiet, the dots, almost every listener had a lower cross than a dot, meaning that they tuned in more bass as the noise came in. And that's also what cars usually do, right? I mean, they increase the volume overall, and they kind of escape the masking of the low frequency driving noise by adding more bass. So on average, our listeners did exactly what the audio system in a car already does. So that's good, and was kind of proof of concept that the adjustments are actually reasonable. But what you also see is that there are pretty large differences between people in how much the noise affected their judgments. So this one listener here in the beginning would rather have the change to be in the order of 14 decibels, whereas others would prefer rather no change in the spectral balance at all. So this we see as an indication that actually you should also take the individual kind of sensitivity to noise into account when you personalize an audio system. On average, cars do everything they can do these days because they would satisfy the average listener, right? So they would put in more bass, but the degree to which they do this, according to these data at least, should be personalized also.
Makes
So
sense.
that's one, I think.
So this was to make sure that, well, I think in the end you're saying that if the adjustments on for a road noise signature of a car does need to be personalized also. It just can't be add more bass because we're driving. It needs to be how much bass based on the individual
if you
preferences.
can,
Okay.
you should do it, because take these extremes. Some would rather not have any more bass as the noise goes up, and others a lot, right? So
Got it.
if you can somehow get to this information, how much sensitivity you have in a specific user, then you should make use of that.
Was this applied in the Mercedes example that you gave us, or is it not yet?
No, it's not yet integrated.
Okay,
No.
all right.
Yeah,
Okay.
but it can be applied across various markets as well, not just automotive. You know, that's the nice thing about it is that you know, you can go from product line to product line, and you know, apply the methodology.
Well, that's a good question. Let's ask that question. Can you do that? I mean, is it pretty universal across different types of audio products? Because that's what we care about. You know, headphones in cars, but also something sitting on the table or a speaker. I think you mentioned the possibility, you know, a mobile speaker that you can carry around that could also do the same thing. So
I think so. I think so. So I will give you an example, and that's the last study I will talk about today on the next few slides. Where we looked at different audio tools. There's one example though where this concept does not work too well, and that is the typical open fitting hearing aid. Where people wearing hearing aids, you mentioned many are dissatisfied. That's true, and one reason is that when they stream music via their hearing aids, it sounds very tinny because most of the fittings are open, which means you can't really produce a lot of low frequency. And then, of course, this concept is heavily based on a low-high frequency trade-off and preference setting. And when you kind of are very limited towards one edge of the spectrum, then this concept has its limitations. So that's one audio product where this concept may not work so well. But in general, I think it's broadly applicable. And there was one study we also published last year where we looked at different audio products and the specific question of, okay, say you have an audio product, say you bought yourself a car and you ran through this procedure, and now your individual settings are already known in general. What if you kind of buy yourself a pair of headphones and access the database where your parameters are already stored? Can you just apply them to the new audio product and automatically adapt it without running through the whole procedure again? So that was kind of the basic question. Of course, all these systems will differ in their acoustic properties, but you may know this difference because they are in the data sheet, and you maybe know the kind of transfer function of these audio systems, right? And if you know this, is it sufficient? Can you just kind of add this together with the individual profile and then have the adjustment automated through all audio products that you are using? So that was the kind of general question.
Good question.
And so, of course, that would be great when you are a manufacturer who has maybe different audio products, soundbars and headphones and in-ears and over-ears and loudspeakers. You could offer your customers a one-time individualization, which is then applied through the whole ecosystem of products. Or you could kind of, I don't know, store the profile, and when your customer buys a new pair of headphones with different acoustics, then this could be adjusted. Or maybe in a car, where personalization, of course, is more and more relevant. Cars may also already know that you are not sitting in the driver's seat this time, but maybe in the rear right seat, and each seat is tuned individually, and then your preferences could kind of travel with you no matter where you are in the car. So it's just a few examples. I'm sure there are more, and you would be the experts to really think about those in the audio product domain. But there are, I guess, different use cases where kind of transferring an audio profile could be beneficial.
Yeah, that would be very, very beneficial. The idea of a cloud-based storage of that personalization and profile, I think, would be very applicable to many products.
Yeah,
I think
and I think
yeah, go ahead.
I was just gonna say, like, there's some other, I mean, besides you guys, there's some other companies doing products like this, and they tend to like I'm thinking of Audio Duo out of Sweden and Mimi Technologies from Germany, and even if we look at the Harman curve, they kind of start at like one segment, and they like perhaps one of them started with headphones, and then they kind of spawn into doing other things. Or I think Mimi did hearing assist for soundbars to begin, and then they've moved into all the different products. So I think this is kind of a theme of trying to accomplish everything with a single solution, but it's not that easy.
Yeah, it's not. And kind of the core question that we tried to address in the study was, okay, does it even make sense to measure only once and then transfer it to different systems? And again, we did some dummy head recordings of transfer functions of different audio systems. We had 4 cars, 2 different types of headphones, so in-ears and over-ears of Sennheiser, and a sound bar. And you see the transfer functions of the system here. So I'm not going into all the details, but for example, the 2 headphones, that's the dashed lines here, they had a very strong bass amplification. The soundbar had no deep bass at all to speak of, and then a strong high frequency amplification, possibly optimized for speech perception. And then the cars were somewhere in between. So they varied a lot. That's basically the point. And we kind of impose these transfer functions onto the violin and cello sounds of the Yosound procedure. We played back these stimuli to our listeners via headphones, so they were not aware which kind of audio system they were listening to at the moment. And yeah, they ran through these adjustments as before, did a test and a retest, and this time it was on the same day. And again, we looked at these self-adjusted preferred levels for the low and high frequency stimuli at a soft and a high playback volume. Again, it was reasonably stable, so there was more scatter than we saw before, but still, statistically speaking, a very significant correlation and no systematic offset to one or the other direction, up or down. And that was true for each listener pooled across systems, and for each system pooled across listeners also. So again, preferences were reasonably stable, I would say.
Yeah.
And then we looked, of course, and that was the main point of this study, how do the different audio systems compare? And because we knew, and also we saw this in the data, that people differed a lot between themselves, we took one arbitrary audio system of the Ford car as a reference. And what I'm showing here is basically the difference to the individual reference of each listener. So the box plots here have a very much smaller range because the kind of individual reference is already subtracted. So the 0 dB line here means that the adjustment for the high frequency stimulus, the low frequency stimulus, and the soft violin and the soft cello would be equally adjusted in the Ford and in the Opel audio system. So that's what this plot tells us. So yeah, that's what I said. So the difference between people here was relatively small because we already had taken kind of subtracted the individual variance by subtracting this reference audio system. But we saw different patterns here. So for example, the BMW audio system was basically adjusted very, very similarly to the Ford audio system. The Opel and the Tesla audio system were, in terms of spectral tilt, also very similar, but slightly softer for the Opel, slightly louder for the Tesla, but no spectral change really. But interestingly, the headphones were adjusted differently, so people tended to adjust more higher level for the high frequency stimuli, both at a soft and a high playback volume compared to the low frequency stimuli for both types of headphones, and vice versa for the soundbar. And if you remember the transfer functions that I showed initially, they were also quite different. And then, of course, we were interested in how does that relate? So how do these individual adjustments relate to the energy that was conveyed by these different audio systems? And because we only have this kind of low and high frequency channel in the individual adjustments, we did a very crude kind of computation of the energy contained in the low frequency part. That's the part which our cello stimuli basically cover, and the high frequency part. And we computed the difference in energy, expressed that in decibels. So that's what you will see on the x-axis here. And we compared this to the self-adjusted difference between the high and the low stimulus. And here's what we found. So that's again box plots across our listeners. And there's a very strong correlation. So audio systems that come with a very strong bass amplification, like the headphones, are adjusted conversely. So people would kind of reinsert the high frequencies and vice versa. A system that comes with very high frequency amplification would be adjusted in the different way. And interestingly, that was true for all but one of our listeners. I don't know what this guy was doing, but in psychoacoustic studies, that's usually what you have. You need to have one outlier, or else the study is not valid. No, kidding. But I mean, that's not unusual for individual outliers. But this is really something where basically everybody essentially followed the kind of compensated for the difference in acoustic transfer function. And that was to us pretty good indication that it seems feasible to just kind of measure or assess the acoustic difference and impose this on the individual profiles, because then you could reuse the individual profiles basically.
So what you're saying there briefly is that if I have a profile on the cloud somewhere and it was made in a car, or if it was made in a room, then you would make a difference check on the next application, whether it's headphones or out some other place. So you have a reference that you've taken once, and then you can compare that to the environment that you're in, and then make comparable adjustments. Is that what you're saying?
Yeah, that's it. There is, of course, one important factor, I guess, which was not included in this study, and that is, of course, different audio systems may come with very different expectations that are not captured by the acoustics, right? So I don't know, there may be vibration, there may be the environment, the haptics, the look of it, and everything. This will also maybe to some degree affect how you would like to perceive sound, which is even more complex to capture maybe than focusing on the acoustics. But remember that in this study, we had people sitting in the listening booth, they had open headphones, they were not aware at all of what system they were listening to. And that was the point, of course, of this study, so they could really focus, were not distracted by anything other than the acoustics. But focusing on the acoustics alone, what you said is right. I'm saying that in practice, it may not be so straightforward, because other factors will also affect the overall user and listener experience in a way which is not captured here. Yeah.
Got it. Great.
Okay, so I think I'm done. So maybe in general, just to wrap up, differences between individuals in terms of preference are pretty large. You have to account for hearing threshold, but it's not sufficient to do so, I would argue. But once you have captured preferences, you can reuse them because they are reasonably stable. When it comes to background sounds, then they should also ideally be personalized in how the audio system adapts to them. And it seems feasible to kind of carry over individual profiles. And with that,
that's great.
Thank you for listening.
No, thank you, Jan. Thank you very much. I appreciate that. And I think you mentioned some papers. Are you presenting, I think, in Warsaw coming up in the month of May at the Audio Engineering European Convention? Is that right? Are you be presenting there?
That is true. I also have a couple of references here for further reading, so you can look
there you go.
Later on.
Great. Yes, that's perfect. Yeah, and hopefully everybody gets a chance to review this as well, just to get into the details one more time. And if you're in Warsaw this summer, at the end of May, come look up Jan at the AES convention there. Thank you so much. That was great. That was wonderful. I think we captured every interesting question we could think of. So thank you. And there's more there. There's more to go through. But I think this has a great understanding of how we can maybe personalize our audio and the complexities and the challenges. But I think they can be overcome, especially if we start to apply, something beyond having learned that it works. We can make it. We can refine it and come up with even more intelligent and artificially intelligent ways to do it, I suppose, as well. So thank you very much. I'll wrap us up here. I'm going to say that once again, don't forget we have some APDA things coming up next month in May. We'll talk about manufacturing in the South Pacific Asia, and then June with the Audio Foundry again. And then we have a Bluetooth LE event coming up in July, as well as we're going to once again talk about tariffs. And if you have anything else you'd like to check in with and have a question for us, leave a comment for us, and we'll be happy to include it in our reply. But with having said that, make sure you do like and subscribe us on YouTube, and we'll keep this video on the channel so you can watch it again and catch up with it and go to the spot that you needed the most. With that, I'll say thank you to everyone, Dave, Steve, Jan, and all those working behind the scenes. Thank you, everyone, and have a good
Thank
day.
you.
Thank you.
Thank you.
Cheers.